In this example, let's examine the coupling effect of thermal and elastic strain. Okay, we have a rigid bar again, ABC. It's supported by member 1, here. So which had a cross-section area of 2.0 square inch, elastic modulus of E equals 10,600 ksi, and a coefficient of thermal expansion alpha. Assume that the A, B, C have all been given, and after load P, it's applied to the rigid bar, and the temperature rises 75 degrees Fahrenheit. A strain gauge affixed to the member 1 measures a strain increase of 1,750 microstrain. Determine the magnitude of the applied P. Okay, this one looks very complicated. Actually, we can try to analyze it as we usually do. Okay, in the beginning, we can do analysis, like how to solve the final problem, one step by one step. Okay, we're requested to calculate the P. So how can we calculate the P? Okay, you need to know the force in the bar 1, right? So if you know the force in bar 1 based on free body diagram and equilibrium equation, then you can solve the P, right? So if you don't know it, then we have no way to solve the P. So we have to solve it from F1, the internal force in bar 1. Okay. So how can we know the force in bar 1? So we need to know what the stress, right? If we know the stress, we can use F equals stress times area to solve it, right? So we need to know the stress in it. Then how can we know the stress? So based on Hooke's law, we can calculate stress from strain. But this is elastic strain, right? The elastic strain of bar 1. But in this case, in this example, the strain has been mixed. Okay, we have known the total value of strain, that is the sum of elastic strain and thermal strain. Okay, so we have to know the thermal strain and then deduct it from the overall strain. Then we can get the elastic strain. Okay, so this is the sequence, the algorithm to solve this problem. So let's see in which step, what kind of equations we need to use to solve this problem. Okay, again, let's review it. To solve P, we need to know F1. Then we need to know sigma 1, then epsilon E1 and epsilon T, right? So here in this step, we just need to use what free body diagram and equilibrium equation, right? So here in this step, we need to use the force equals stress times A. And here for this step, we need to use Hooke's law, right? And in this step, just the equation we just defined, right? The overall strain equals the total strain equals the sum of them. So the elastic strain can be calculated from total strain minus thermal strain. Okay, we will need to use such 4 sets of equations to solve this problem. Okay, let's see the first step. Well, we will focus on here. Right, so first of all, we need to know what is the thermal strain. Okay, what is the thermal strain in this case? You can see we have known the alpha, right? Alpha is here. Then do we know the delta T? Delta T is here, right? So easily the thermal strain can be calculated from alpha times delta T, that is 12.6 microstrain per degree Fahrenheit times 75 degree Fahrenheit, then that would be 945 microstrain. Then the overall strain, total strain had been given. That is here, right? That is the sum of them, the sum of thermal strain and the elastic strain. Right, that is 1,750 microstrain. So what is the elastic strain? Elastic strain of bar 1 equals total minus the thermal strain. Right, that is 1750 minus 945, and we got 805 microstrain. Okay, then the second step will be here, right? So the strain, the elastic strain of bar 1 equals sigma 1 over E, right? So sigma 1 can be calculated from E times epsilon elastic strain times elastic strain of bar 1. So the E is there, 10,600 KSI times 805 microstrain. So this will be 8.533 KSI. Okay, so in the third step, we're looking at here, so we can calculate the force in bar 1, F1, right? F1, that would be sigma 1 times A. Right, the sigma 1 has been calculated here. This is 8.533 KSI times the area, 2 square inch. Right here, 2 square inch. So we got the answer would be 17.07 kips. All right, so here we have just the last step to do. This is the fourth step. In the fourth step, we'll only need to use the free body diagram and the equilibrium equation to solve it. Okay, so look at here. When we have this bar, just cut it free, and we have a pin support at A. So you have two of them, FAX, FAY. Then at point B, you have a P here. At point C, you have a F1 here. Okay. Then, of course, you can write 3 equilibrium equations. Add Fx equals 0, so you can denote that Fax equals 0. Then Fay equals 0, you can get an equation but not solve it, since one equation, 2 unknowns. Right, this the third equation will be sum of m about point A. If we set just MA about point A equals 0, right, we can solve it directly, right? Since we have only 2 moments, that's from P and from F1. Right, we can write one equation and we have only one unknown. Okay, since here if you select point A, you will be able to remove Fay, so only one unknown left. So we can solve it through one equation, right? We only need this one equation, right? How to write this equation, the equilibrium equation? I just ma equals 0. From here we can get an equation that is p times a minus f1 times a plus b equals 0, right? So p equals f1 times a plus b over a. f1 there, 17.07 times a plus b is 50 plus 30 over 50. Okay, here we get 27.3 kips. That's it.